Recording in progress.
Hi, good morning, everyone. Thank you for joining us. So for today's presentation, we're doing a webinar. One second, just getting the room audio. We're doing a web presentation on power semiconductors. Today's webinar is Advancing the Frontier, Challenges and Opportunities in the Power Semiconductor Ecosystem. Today's agenda is going to consist of two parts. The first half of the presentation is a keynote covering the power semiconductor market. Our presenter is going to be Paul Pickering. The second part is going to be a panel discussion with 4 member companies. And finally, at the end, oops, one second, let me share my screen one more time. And finally, we'll end with a quick conclusion, referring readers to additional resources and materials. So with that, we'll introduce our keynote speaker. So Paul Pickering is the research director of semiconductors at Omdia, where he leads a team of analysts across power semiconductors, automotive, industrial, and microcontroller units. Paul is an electrical engineer by training with 35 years of global experience. He has 20 years in the semiconductor industry and nearly a decade in the automotive electronics. He's lived in the United States, UK, and Japan, and he offers a seasoned and diverse perspective on the evolving technological landscape. So with that, we'll hand the presentation to Paul.
Thanks, Greg. Good morning, good evening, good afternoon to everybody. I've only got 30 minutes here, and this is going to be at a fairly basic level, and there's a lot to get through, so let's get going. First question we need to ask, next slide, please, is a really basic one. What is power? Well, electrical power is, as you see there, this is the only equation in the whole presentation, I promise, is expressed in watts. Power is volts times amps. So, for example, 1 kilowatt power could be expressed as 400 volts at 2.5 amps, or 48 volts, 21 amps, or 1 volt at 1,000 amps. So as a means of comparison, a typical single-family home uses about 1 kilowatt up to 5 to 10 during peak times. An AI data center rack can use as much as 150 kilowatts, typically operating 24/7, as we know. And a typical hyperscale data center consumes the equivalent, as it says here, of about 50,000, 100,000 homes, which is, a small town. And this is kind of important because 1 kilowatt is about the power that's used by a single GPU. And so you can imagine that in a hyperscale data center, there are many, many GPUs. So that's where they use a lot of power. So what is a power semiconductor? Well, a power semiconductor, as it says, its job is to regulate and control electrical power in the most efficient way possible. And, it's in plain language, like it says, it's the component that controls energy, not data. Obviously, a GPU is primarily concerned with moving data and manipulating data. And as such, the power semiconductor is not a GPU. It's not a processor. It's not an analog processing block, such as an op-amp or a data converter. And it's also not a memory device. It's different from all of those. And because it's different, there is a complete ecosystem set up to optimize power semiconductors for the control of electrical power, as opposed to the manipulation of data. And that leads to differences, as we'll see in a little while. The reason that this controlling of power is important is that most power is transmitted at high voltage, low current. You think about the hundreds of kilovolts, an electrical grid, the 800 volts of an electric vehicle battery, and the trend is going higher and higher in terms of the transmission and lower in terms of the processing. So processing device has gone from 5 volts to 3.3 volts down to less than 1 volt. So that's very important. That makes the job of the power semiconductor crucial because it has to convert essentially that a high voltage, low current to a low voltage, high current. It's a very important job. Next slide, please. They are essential elements in almost all electronic devices. This is a screenshot of a photograph that we took at APEC last week in San Antonio. This is from our friends over at Texas Instruments. This shows a board of a GPU with the power supplies all around it. The GPU is not shown, but you can see all the round dots in the middle. That's where the GPU would go. Look how many power devices are needed around that in order to supply enough power for a GPU. So a typical server board, as we say here, is a 48-volt supply. A GPU might require less than a volt, 1,000 amps, which is a 1,000 kilowatt, 1,000 watts device. And we need multiple semiconductor stages to convert that 48 volts to 0.7 and supply enough current. So we have several stages in sequence to get from, for example, 48 volts to 12 volts to 6 volts to 1 volt. And that requires a lot of power devices for each GPU. And as I said before, they have their own unique ecosystem to provide that. Next slide, please. Why are they different from digital products? We have a few slides here talking about some of the differences. First of all, they use a broader range of materials. The high-speed digital stuff that we all hear about is made exclusively from silicon. Silicon has been around a long time, 50 years, and it is very well optimized for this type of high-speed digital manipulation. It's still used in power semis, as you see here, automotive, industrial, and many legacy applications. But more recently, power semi engineers have discovered or developed two what we call compound semiconductors, silicon carbide and gallium nitride being the most common. Those have, as you see, higher voltage ranges. They're not as mature, 25 years in the case of SiC, and medium, 10 to 12 years in the case of GaN. And they have different applications where they have found a lot of attraction, a lot of companies designing with those devices. There are others on the drawing board. As you see here, gallium oxide, diamond, etc., in order to try and push the voltage range even higher than we have now. Those are typically in the R&D stage. The cost is, not surprisingly, at the moment, very, very high. So that's kind of a summary of what we have in silicon. Different processes. One of the characteristics of the power semiconductor market is that products have a long lifetime. It's no exaggeration to say that many devices have been in production for over 50 years. I mean, almost without changes for the whole period. They use processors that are optimized for delivering these high voltages and currents. We have more processors than you would find in a GPU or a microprocessor or a memory device, as you can see here. These devices have various combinations of characteristics, but together they allow designers to combine these various functions, especially BCD, which is what we call a mixed signal process, which allows them to combine precision functions, analog digital control into designs that are intended to deliver power to the load, whether that load is a motor or a GPU or whatever. And they're not compatible with the processors we'll be talking about for the high-speed digital. They use CMOS, and that is optimized for high-speed switching. And therefore, it's by extension or by implication is not optimized for switching large amounts of power. Next slide, please. Also, power semiconductors use different manufacturing lines. We're not going to go through all of this, but you can see on the left is the typical fab line of power semi fab. It's a fabrication we're talking about. And on the right is the typical characteristics of a digital high-speed fab line. You can see there are multiple points where they differ. A lot of this is the province of semiconductor engineers, but you can see the digital one has a great deal of variation from the analog, from the power semiconductor line. And as it says at the bottom, they're optimized for different purposes, optimized to move and control energy versus optimized to move data very, very fast and manipulate it very, very quickly. This is just an example of some of the power semiconductor devices. These are discrete devices that we cover at Omdia. We also have about 20 power IC devices that we cover and track. And you can see there's a lot of different variations, a lot of different flavors within power semiconductors, split here broadly into the three different commonly used silicon materials: silicon, silicon carbide, and gallium nitride. And you'll see there are some devices, for instance, HEMT, that are exclusive for gallium nitride, and there are some devices such as JFETs and MOSFETs that are used for different types across different materials. And again, there are multiple ICs that I didn't add for the sake of brevity, but a lot of variety within the power semiconductor universe. And each one has a slightly different set of characteristics and features that make them valuable for particular applications. Next slide. Finally, different packages. You can see all these packages over here on the right cover a wide range of applications. Again, it's the same idea. Power packages are designed for maximum current, maximum voltage, and also to remove heat, because any power that's not used to transmit to the load generates heat. And that is a big problem for power semiconductors, because silicon above a certain temperature stops working. So if the junction gets too hot, the device will just stop working, or even perhaps melt down in a catastrophic failure. So you can see that a lot of these devices are set up, they have these little metal tabs on the top, which are set up to remove heat more efficiently from the silicon that's within. Some of the differences here from standard digital logic are noted pretty much across the board: thermal design, electrical integration, lifestyle. We also have packages optimized for these new materials that I've talked about, SiC and GaN. This is an area of active research. Here are some of the current trends. We're always trying to make power packages more efficient in terms of removing the heat. We're starting to combine power semiconductors into modules. Looks like I forgot to finish the sentence. Vertical power is an emerging trend, and is something that is again one of these technologies that aim to get power more efficiently from the power device into the GPU. The point with vertical power is mounted typically directly under the GPU on the other side of a circuit board, which is the shortest distance, the closest they could possibly get to transferring the power from the power semiconductor into the GPU. And that is a very emerging trend. In the APEC last week, many manufacturers were demonstrating their versions of vertical power, and it's definitely an area that you'll see a lot of devices being introduced over the next several years. Next slide, please. Where are they used? Everywhere. Short answer. These just a sample of some of the applications. The biggest one for power ICs is smartphones. Another huge application is EV, electric vehicle traction inverters, and immense number of applications in industrial. And then finally, government military is an important market, very specialized devices for this, but things like electronic warfare, military radar, and secure radios are large users of these devices. So really it's across the board. Next slide, please. So how is it used? Well, who manufactures them? As you can see here, it's very fragmented. I've listed the top 10 companies here. Top one is 12% market share, and it goes down quite slowly after that. Still, with top 10 devices, you have almost half of the market is other companies. And that's not true of other markets. If you look at GPUs, I think maybe you have three or four or five. After that, that's 90% of the market. And so power semiconductors is very fragmented. As you see here, the top 10 are basically mostly US and Europe. And as we go down the list, you'll find that US companies and Europe companies increase slowly. But what we see is that China increases more. And if you go down below the top 40, there'll be a lot more Chinese companies to the point at which when we get down to the total number that we cover, which is over 100, it's basically half Chinese companies, which is significant, which we'll see a little bit later. And in terms of how do they sell the products, they sell through direct and through distributors who are the middlemen of the semiconductor supply chain. And many of them are also commodity products. And that means that many suppliers produce very similar or even interchangeable products that users can take advantage of. And some of these companies, the number one, which happens to be Infineon, which is no secret, is very prominent in both power discretes and power ICs. Some of the other companies down the list primarily focus on one or the other. And so that is one of the characteristics of the market. Next slide, please. Take a look at the power conductor, the semiconductor market landscape. Next. We're not going to go through this, just gives you an idea of some of the things we track. Every market has a different set of characteristics. Wireless communications used to be the largest segment, but that is being surpassed by computer and data storage because that has a compound annual growth rate of 13%. As we know, is due to AI fuel growth in data centers. Industrial segment, automotive are both fairly slow moving segments. As we know, the automotive power IC market has gone through a bit of a slump recently because EVs production has slumped. But if you have more interest in knowing more about this, please contact me after the discussion. Next slide. Okay, by device, we have three things that we track: power ICs, power discretes, and power modules. You can see here that the growth rate is between 2025, 29 is 7.1%. Power modules is outpacing the growth of the rest of the market due to EV traction motors. And power discretes is also driven by that, but power ICs is going to be driven by a large growth in the computing market. Next slide. As you see there, that's a comparison of the markets for the different segments for power ICs. You can see how much more active is the activity in computing and data storage. Next slide, please. Compared to other categories, you can see here the split by market segment is currently computing is only 11%. We see that increasing tremendously over the next 5 years due to the rise, of course, in AI data centers. Next slide, please. So what are some of the challenges that we face in power semiconductors? Next. So we're all familiar with the CHIPS Act and the equivalents in foreign overseas, China and EMEA. Broadly speaking, here are some of the takeaways that we have for those different acts. They have different focuses. For the US, they're important. Restoring advanced node leadership. So they spent a lot of time trying to attract and trying to support the fastest nodes, which are, as I say, GPUs and so on. Focus is on chips critical for AI defense, high power computing. China, on the other hand, is aiming at semiconductor self-reliance, and that's a national security priority. China has been subject in the past to restrictions from overseas on the purchase of devices, equipment, IP, and so on. And so the state is investing a lot of money in supporting the semiconductor industry. And so in a sense, cost is somewhat secondary. EMEA is sort of in a middle position. EMEA wants to support their own industries. Europe has a lot of automotive and industrial production. They're used to collaborating. They not necessarily look for independence. So the goal is to reduce dependency and focus on their selective set strengths. Chips essential for the industries that they are active in. And it's coordinated across various states, as we know. Next slide. Okay, so this is a summary of what I just said. You can see that in terms of support for power semiconductors, it doesn't, the Chips and Science Act, I would say, does not concentrate specifically on power semis. It focuses primarily on advanced logic. There is some funding that is being allocated for mature chips, which power semiconductors are a mature technology. China is treating power semiconductors as more of a strategic infrastructure issue. And Europe, as I said, is focusing explicitly on the areas where it is strong. So next 5 years, several challenges that we see, global cost pressure, Asian competitors, as we're all familiar with, benefit from lower costs. That is putting pressure on US and European manufacturers to try and maintain profit margins. We need to reduce our dependence on overseas wafers and substrates because that creates vulnerability. There's a well-publicized skills gap in the workforce that we need to fix. The problem with power fabs is the lower capital expenditure, but much longer lifetime products. And so from the point of view of the market, they deliver lower returns than digital fabs. And transitioning to SiC and GaN will create execution risks to make sure that the quality is up to where certainly the automotive industry will needs. And finally, many of the products exhibit volatility in the markets. We're seeing an industrial slump in the automotive market, and many of these markets are cyclical. So that can lead to either overcapacity or oversupply. Next. Here are some imbalances in the power semi, which are causes of stress, potential problems. The big one that I like to point out is US companies have 36% market share, but only the US market is only 13% of the revenue. Conversely, Chinese companies have 13% market share, but market is about 41% of power semi revenue, which means that one of the first priorities for Chinese companies is increasing their share of their domestic market. In 2022, as you see here, 19%, going up to 24%, and now it's up to 28%. And this is a pattern that's been repeated in other types of semiconductor markets. They can't really compete yet in the fastest logic devices because they don't have access to the equipment, but they can certainly purchase many of the pieces of equipment or manufacture them that are needed for power semis. So that is an ongoing threat that we're keeping a close eye on. Next slide. Finally, I think this is finally, a supply chain is only strong as its weakest link. We have all remember in COVID these photographs of automobiles being stuck in the parking lots of General Motors and Ford, Toyota because they couldn't get $50,000 car being stuck for want of a $1 part. With explosive growth in AI, I'm wondering whether in 2031 we'll have the thing that you see here, which is a data center full of racks waiting for server boards, which presumably are waiting for $1 power semi parts. Well, let's hope that doesn't happen. And that's one of the things that policymakers and the companies on this call and elsewhere can act to mitigate, and is a source of attention in the executive suite. I think that is it. So thank you very much. I appreciate the time. Sorry I went a few minutes over, but if you have any questions, please contact me or get in touch through Greg, and we'd be glad to try and help out. Thank you very much. I appreciate it.
Excellent. Thank you, Paul. One second. So just for the audience's awareness, we do have some additional materials. Oops. So we have some additional materials. If folks are looking for more information from Omdia on the power semiconductor market, you could purchase their research, their Power Semiconductor Intelligence Service, their Wide Band Gap Power Semi-Intelligence Service, or ultimately scroll their entire library of solutions. Once we distribute the presentations, these text links should navigate you to their page. With that said, we will pivot to our panel discussion. Our first panelist is Leonard Stargott. He's an ADI fellow at Analog Devices. Leonard specializes in high-performance power integrated circuit design and has been a driving force behind the Silent Switcher technology platform. With 2 decades of experience, his expertise spans gallium nitride DC to DC conversion and advanced packaging techniques for data center applications. Our second panelist is Dinesh Ramanathan. Dinesh is the Senior Vice President of Corporate Strategy at onsemi, where he leverages 25 years of experience in hardware, software, and semiconductor design. Dinesh is a former CEO and co-founder of NextGen Power Systems. He holds a PhD in Information and Computer Science with a deep background in vertical gallium nitride technologies. Excuse me. Our next panelist is Jeff Halbig. Jeff is the Product Marketing Director for Power and Discretes in the Americas for ST Microelectronics. Jeff focuses on power discrete technologies across the automotive, industrial, and power electronics segments. He is an MIT-trained electrical engineer with over a decade of experience and at least 8 years of senior design experience in the telecom and industrial power supplies markets. And our final panelist is Pradeep Shenoy. Pradeep is a compute power technologist at Texas Instruments. Pradeep leads the systems engineering team focused on data center solutions. He holds a PhD in electrical engineering and is a prominent figure in the power electronics community. He serves in leadership roles at the IEEE's Power Electronics Society and the Applied Power Electronics Conference. So with that, let's pivot to our questions. So our first question that we have for our panelists is the future of power electronics still an EV story, or are hyperscale data centers and the power wall of AI becoming the new dominant drivers of demand for silicon carbide and gallium nitride adoption? Our respondents are going to be Leonard and Jeff.
Hi, everyone. I'm Leonard. Great to see the audience here. Seeing a lot of familiar names in the participant list is fantastic. Hello. So for question one here, it's an extraordinary time. On the one hand, we're seeing great growth in electrical vehicles as battery technology improves and helps the tipping point come in terms of beating the prices of gasoline vehicles. So in a lot of countries, we're seeing a greater mix of automotive sales go to electric vehicles, and each electric vehicle is probably worth a few $100s, if not more, of power electronics. And in there, there's two systems. There's the 400 or 800 volt system, which is overwhelmingly becoming a wide band gap for traction, for EV charging, etc. And that trend was kicked off very popularly by Tesla 7-ish years ago, where at those voltages is very favorable to have wide band gap there. An interesting thing is the electrical charging infrastructure is pacing this whole revolution. And so in there, it's not as popular, doesn't grab as much headlines, but the charging infrastructure is an absolutely critical portion of electrical vehicles and also a huge consumer of various power electronics there. And so the EV story continues, but interestingly, there's only so many cars and people that can fit on the roads. And so while the overall car sales remains paced It doesn't change hugely year to year. That mix is changing towards electric certainly pretty quickly in many countries. So this slide here, however, I think is we're living in extraordinary times as far as the build out of data centers goes and compute. For many, many years, compute has been roughly a few percent growing market every year to serve websites and do corporate SaaS, things like that. And so overall, compute was well supplied and it was paced by demand. And in the last few years, since the ChatGPT moment, the usage of high performance computing in the form of GPUs, NVIDIA certainly being one of the top producer, but also many others like Amazon and Google producing many servers. The total consumption of power for compute is actually making a big dent in the whole national grid. If you kind of look at this chart, it's almost unbelievable. We're seeing that in the next few years, it may get to 10 or 20% of the total grid power is going to be spent on compute. And all of that has to go through power semiconductors one way or another, as typically. So if you guys have a look at this slide, I want to jump to the next one to show you there. So see, that whole consumption, if we end up to 10 or 20% of US wide, and maybe at some point a few of the leading countries will end up with 5, 10, 20% of their whole grid going to compute, you'll generally see a similar picture where generation happens at very high voltages. It could be power plants, could be storage, and the very unusual way that compute uses power all goes down to 1 volt. So I always call it the 1 megavolt to 1 volt waterfall there, where you have to get from generation distribution to consumption. And so it's a kind of a fun picture. And there's a few things that are happening here that are new and very relevant to wide bandgap. One thing that's happening is kind of the medium voltage conversion in the 10 to 50 kilovolt range. We're starting to see a half dozen startups that are becoming competitive in solid state transformers, where rather than buying truckloads of iron transformers, they're actually switching regulators, but stacked to handle many kilovolts. And those mostly are silicon carbide. So that may be a surprise demand that bursts on the scene as this revolution really gets going. Another thing that's very important is you'll see I have a little battery there. The U.S. power grid produces about 1 terawatt peak at the moment, and that has to handle all kinds of weather conditions, et cetera. But at night, at standard load, we're only maybe at half of that capacity. So we've got about half the grid, so 500 gigawatts worth of generation not being used, which could be used for data centers. However, you need to be able to store the few hours of peak demand during the day. And so, as in EVs, batteries are key to the whole drivetrain. In the case of data centers, batteries are key to be able to extract far more production capacity of electricity from the existing grid. And so if you could store those 4 or 5 hours of peak capacity in a battery system, it dramatically improves how much total power you have available for data centers. So batteries are a big story for data centers, and certainly going from 800 volts down to 1 volt, 100% of that power ends up going through various semiconductors, and many of them are going to end up being wide bandgap. So that's roughly the picture I wanted to paint. So let's let the next panelists participate here. I think Jeff, go ahead.
No, thanks, Leonard. No, that was super interesting, and I agree a lot with what the picture you're painting there. So what I like about this question is it's saying EV was really pushing adoption of new technologies before. Has AI become the new dominant force for driving adoption? Well, the question is, what is adoption and what is driving? So I've got a couple different takes on that one. But first of all, just for the let's say non-electrical engineers out there, just to frame what silicon carbide and gallium nitride are. These are composite materials that are known as wide bandgap materials for creating power transistors. And power transistors are the switches that are used in power systems to kind of shape the energy the way that you want it. Leonard just showed the grid to core process there. So once you got to that 800 volt point, you said 100% of the energy is going through power semiconductors. Absolutely correct. So what's happening there? These power transistors are switching to move voltages down at the same time moving currents up to maintain the power that's moving through the system. So these switches are super, super important to designing the systems that are powering everything that is electronic in our world. And wide bandgap has the advantage of being able to operate at higher voltages, higher temperatures, switch faster, and generally be drivers of more efficiency and power at scale. So as you have more adoption of wide bandgap devices, you can scale things to higher powers without losing so much energy. And that's really what the competitive advantage of using these materials are. Now, their use case is a little bit different between EV and data center. So EVs had their moment, very proud with ST Microelectronics in driving Tesla to the adoption of silicon carbide and the electric vehicle ecosystem. And really, it was about extending the range of the car. You know, the car was a problem that was sort of self-contained. You had to have this thing that requires so much energy to transport people around. And yes, there are peaks and valleys and different levels of performance, but largely it was a well-defined problem. You know, you've got so much energy storage, you need to consume that energy to transport people, and that problem has been solved. And silicon carbide was crucial to solving that. We've got cars that can run about the same as a gas tank, 400 miles, 450 miles, depending on the model. And really the adoption of continued adoption, as Leonard alluded to, as part of an energy infrastructure, installing enough charging stations to replace gas stations and things like that. So when it comes to the EV, the value is scale. There was almost 100 million cars, what we call light vehicles in the industry, sold in the world last year. Now you sell 100 million of anything, that's going to be a driver for adoption, right? We haven't gotten to 100% electrification. This is an annual basis too. You're creating 100 million new cars every year. You're going to have this humongous amount of semiconductor that's going to be burned through on an annual basis. So it's hard to compete with that when you talk about driving adoption. But as I mentioned, the problem's largely been solved. So it's not going to really drive a whole lot more innovation, I believe, in wide bandgap, but more just driving down in a race to commoditization. And as you commoditize the parts and get more efficiency in producing them, then that opens the door to it being affordable enough for other industrial applications and then the adoption of wide bandgap en masse. Now, data center is a little bit different because it's requiring a value proposition of really dollars per watt in power density that you want. Efficiency is the king here in order to save cost, to save the load on the grid. And it is driving innovation, I would say, rather than adoption of semiconductors for GaN, for the rack level power conversion, for very high voltage silicon carbide on the grid level power conversion, in order to bring to reality this these new type of architectures that are being developed with power semiconductors today. So the way I look at it is, there's this humongous market that's driving scale in EV, and then there's this market that's driving innovation and value per watt, particularly with GaN in the data center architecture. And so that's kind of the trade-off for two. So they both have very important roles to play in driving semiconductor adoption in the future. Thanks.
Excellent. Thank you, Jeff. Thank you, Leonard. So for our next question, our respondents are going to be Dinesh and Pradeep. The question is, we're seeing rising demand for semiconductor products, especially from AI end uses. How will this growing demand impact the power semiconductors market?
Okay, so so the way we believe that the rising demand is going to impact the market is twofold. One is there'll be significantly larger amounts of innovation that will actually come about in this particular market, primarily to deal with one of the key metrics that Jeff was talking about, which is power density. So power density is how many watts can you actually squeeze in a volume of area that's actually specifically set up in front. So the more power you can actually extract from that volume, the denser the power supply or the power equation ends up becoming for that particular application. So power density is going to be a really important part in the requirements for AI data centers going forward. The second part that will also happen is innovation will kick in areas in which you have to bring an ecosystem around these power semiconductors. So I fundamentally believe that not only do we need to focus on only the power semiconductors, but also the entire ecosystem around it. And that ecosystem around it has three components. So there's the power electronics component, which is devices that are made from gallium nitride, silicon carbide, continuing silicon adoption as well, putting them together with drivers and controllers. There's a second pillar for power density, which happens to be mechanical design, which is how do you take multiple of these power semiconductors, put them together to realize resistances which are significantly smaller. Part of this, Paul alluded to when he was talking about modules. So module design and module creation is primarily a mechanical engineering exercise. And then how do you construct those modules in an effective manner, making sure that you're reducing the inductance of those modules as well as reducing the resistance pretty dramatically. The third axis, which also Paul alluded to in his presentation, is thermal engineering. So we actually have to make sure that we can pull heat out of these modules or the power semiconductor in a much more effective manner, because pulling the heat allows us to run the devices cooler, potentially pulling more power from them, or making sure that they're reliable over a long period of time. So I think the entire ecosystem around the power semiconductors have to evolve in order to meet the demands that we are seeing from primarily the AI end users. And innovation on all these three axes are going to be critical to get us to where we want to go.
Yeah, those are some great comments from Dinesh and the other panelists. So from my perspective, and if I can go to the next slide, just to kind of further paint that picture that they've already been sharing, we see semiconductors across the whole range of applications here within the data center, right? Everything from your grid infrastructure to what's going on inside of your IT rack. The other thing that I want to highlight is, we talk about all this power getting into the data center, but where's that power going? Ultimately, it's generating heat, right? So we need to be able to also cool the data center. So that's where, cooling distribution units and things like that are also very important. There's a lot of semiconductors that go into that as well. I totally agree with the comments before about efficiency being critical and having density, size being very critical, thermal management, all these sorts of things. What I see the real, I think, impact to the power semiconductor market is going to be how the architectures change. And if you go to the next slide, I have kind of like an overview of that. Hopefully we can go to the next slide. There we go. Sweet. So when we're talking about the power levels, we're talking about orders of magnitude increase, right? So when you go today, Paul mentioned this, it's like 100 kilowatts is what you'd have in an IT rack today. This is like, let's say, the Gen 2 on the left. But as we move generation over generation, we're now seeing hundreds of kilowatts, probably like around 600 kilowatts, and we're talking about megawatt level and above. So this is an order of magnitude higher power level we're talking about here. And so what that requires us to do is a strategic shift in how we are designing the actual power architecture itself. And we need to do it in a way that reduces the losses along the way. You want to get energy from wherever the source is to wherever it's got to go, powering these AI processors. So that typically means how can we reduce the number of conversion stages, all these middlemen that, take their cut in the middle, so to speak, in between. And we also need to be able to distribute power efficiently. So one of the big topics of conversation is going from the 48 volts that Paul mentioned earlier to 800 volts or plus or minus 400 volts or things like that as we go to future generations, let's say generation 3 on this slide, where we've moved a lot of the power conversion out of your IT rack into an adjacent sidecar power rack. And then even further, Leonard talked about solid state transformers and how that's going to be impacting how power is delivered. And really, I think what we'll see in the future is high voltage DC. When I say high voltage, I mean like 800 volts or something like that being distributed throughout a data center. So these architectural changes are going to be have a very meaningful impact in the power semiconductor market.
Okay, so moving on to question number 3. How are power semiconductors different at the edge versus at the data center? Pradeep, do you mind kicking us off?
Yeah, sure. So, certainly in the data center, you're looking for this, some people call it an AI factory, right? It's a lot of power, a lot of compute, all that kind of stuff. When you talk about the edge, this is an application like, say, maybe a car or a robot or something that typically will have some limited power supply, right? It might be operating off of batteries. And so all of those designs have certain constraints. And you want to see, we see a lot of emphasis, I think, on integration, reduction in size, also having low standby power, very high efficiency across a wide range of conditions and environments. One of the big applications at the edge is inference, right? So in a data center, you will often train these AI models and you will do some inference, which is using the AI models. But at the edge, you're going to have a lot of edge-based inference. And so you need to power these inference activities in a very efficient manner.
Dinesh, do you mind jumping in?
Sure. Yeah. So I agree with the comments that Pradeep made. I think the amount of work that can be done on the AI edge is going to be dictated by how much power is actually going to be available in those pieces of equipment that we kind of put together. So, I mean, we've already seen this happen with the amount of compute that we had in the cell phones. I mean, if you take that as one of the primary example. Today, your cell phone battery will last for almost a week without you actually having to do too many things to it. Originally, the cell phone batteries used to last maybe 2 days, and then you had to kind of plug it in to get charged in again. So I think battery capacity and battery management will become an important part of how the edge gets managed, because the amount of power that we can pull on the edge will determine what type of functionality we can actually have on the edge. The AI data center is very different than the edge, as we kind of talked about, primarily because in the AI data center, you have high voltage rails that you can actually drive down to low voltage. So when you go from, let's say, an 800-volt bus architecture down to a 1 volt to supply the GPU, you're reducing the voltage, but the amount of current basically linearly increases from there. So 800 times more current will run through the 1 volt system than will run through the 800-volt system. But you can't do these type of modifications in an edge application, because power there is usually going to be or will be restricted to either a battery or some kind of low end power device that's actually going to get plugged in. So you're going to have to make sure that battery management is well taken into account, batteries are well taken into account, and the power requirements for any compute that happens at the edge is going to be significantly lower with low power modes and the ability to control how much power can be pulled, maybe in spikes. So all these interesting things that we have done before to make sure that the cell phone infrastructure kind of got us to where we are at this point in time will get deployed there as well.
Excellent. And Leonard, you want to jump in?
No, you guys continue. Go ahead.
Okay. So for we're going to pivot to question number 4 now. So how are power semiconductors evolving to meet AI's rising energy demand? Jeff, do you mind jumping in to start us off?
Yeah, absolutely. So I've got to do a call back to a couple of my other panelists to set up the problem here, because the semiconductors are going to evolve to meet the challenge. And really, it's a two-factor thing. So the one that Leonard introduced is the challenge of getting energy from the grid to a central point. So you've got the high power generation, high voltage generation that needs to go through multiple different steps down to a GPU, which is now consuming 1 kilowatt plus amount of power. And so along that way today, you're losing 10 to 15% of that energy is heat. And that's not acceptable as we're trying to scale these things up. We need to save every joule of energy that we can. And semiconductors, as I mentioned before, are the ones shaping that energy, very, very critical to evolving that. And then Pradeep talked about, well, we're shifting our architectures in order to meet some of those challenges. And those architectures are really based upon what the semiconductors are capable of today. And the primary drivers of those are GaN, of course, and silicon carbide. So the real evolution right now is taking advantage of the 700-volt GaN, the 1200-volt silicon carbide that we have. Mechanical redesigns are very important. People don't often think about how you package these semiconductors is critically important, because you have to get the heat out that they're dissipating. So we see trends in dual side cool packaging, very low profile packaging in order to meet power density requirements on the racks. The dual side cool helps to get power not just from the semiconductor itself, but also from the total system. For instance, we designed a power delivery board where the semiconductor itself is the heating or the cooling conduit from the PC board where the magnetics are embedded. Get the heat out of those magnetics goes through the semiconductor. So these are some evolutions. And then evolving silicon carbide to very high voltages, the 2.3 kilovolts, the 3.3 kilovolts are enabling the solid state transformers that have already been discussed. And these are systems that take those big, bulky linear transformers that you're used to seeing up on the power poles and converting a whole bunch of steps of power conversion and condensing them into one. So now you can go from medium voltage on the grid right to the 800 volts. That's going to go right into the data center rack instead of having 2-3 different steps. Also, the evolution of the solid state transformer enabled by very high voltage silicon carbide gives you intelligence. So you can do some load management. You can do safety precautions. You can do all sorts of intelligent power design with power semiconductors rather than having passive components. And then as we look to the future in the 2030s, we'll continue to evolve and adopt ultra wide bandgap devices, things that are in research today with diamond, with gallium oxide, aluminum nitride as the materials. Of course, that's still a little ways out. I mean, I never say that we're moving slower than we are because things are moving at an exponential rate. But, in the early 2030s, maybe we'll get past the manufacturing scales of these ultra wide bandgap materials, the thermal management, the material defects that plague us today. But for sure, innovation is required. We need to invest if we're going to meet the energy demands of the world, not just AI, but really the electrification of everything.
Excellent. Thank you, Jeff. Dinesh, would you like to jump in as well?
Yeah. So I'll take Jeff's cue on the electrification of everything and kind of talk about that a little bit more. So I think the comments are all in the direction that the technology is headed, driven primarily by AI's rising demands. But then there's also this EV infrastructure that we shouldn't forget, because today, while the EV sector might not be the hottest sector in the market, it definitely is a change that's kind of here to stay, and probably here to stay for a very, very long period of time. So taking both those things into account, I think there's going to be evolution in how do we make these semiconductors operate at higher and higher voltage, because the higher voltages we can operate, we can start pulling power from the grid into the data center in the most effective manner. Jeff talked about that. Silicon carbide today is the way to get us higher voltage. At onsemi, we've invested in this technology called vertical gallium nitride, which also allows us to get higher voltage with gallium nitride. So today's lateral gallium nitride products are typically at about 650 volts. We've made vertical gallium nitride devices that can withstand 4,000 volts. 1200 volt is the one that we're actually looking to put into production right now. So these devices are much smaller. Their capacitances are smaller, so you can actually switch them faster, which means you can shape the way the current actually needs to come out from these power systems in a much more effective manner. So that's one innovation. The second innovation, which also Jeff kind of alluded to as well, is thermal management. So you have to make sure that you can cool these power semiconductors down much more effectively. So we've been looking at can we use diamond for cooling some of the power semiconductors, especially when you're pulling a significant amount of power from these devices, pushing them into the data center, especially the 800 volt, down to 6 volt infrastructure that some of our customers are actually asking us to work on right now. The third aspect, which I've kind of alluded to earlier as well, is making sure that these semiconductors are balanced with the mechanical engineering part of constructing the packages that go around it. And then with that, making sure that you have the ability to pull the heat out from these modules or packages that you put together, because that's how we will get to higher and higher power density. And I think power density is what's going to keep driving the evolution of all the semiconductors in this space and the ecosystem that goes around it.
Excellent. So with that, we'll pivot to our lightning round, assuming I can get the slide working. Okay, so this is a question for each of the panelists. What do you think policymakers misunderstand about the power segment and foundational chips at large? We'll start with Leonard.
Sure. One perspective is power is very much a B2B kind of issue. It doesn't immediately end up on the screen of consumers. However, like the circulatory system or your mitochondria or something like that, power is absolutely underpins everything in modern technology. And one thing that is probably worth trying to peek around the corner of what may happen is if AI sort of delivers on its promises of various autonomy, it's eventually going to end up in robotics and automation, where it interfaces with the real world. And at that point, it becomes an absolute sort of linchpin to the whole AI revolution in general. And because we're starting to get to 10-20% of the total grid being consumed for compute, it becomes an absolutely foundational technology for the future of the country. And so many ways to invest in it with various academic, government, development, manufacturing partnerships probably has far better return than is generally understood in the public eye, I think.
Excellent. Dinesh?
Yeah, so I think there's a lot more work that needs to be done with power electronics, and I'll try to say it in the following way, right? So power electronics, by its sheer definition, hasn't been the sexiest field that has been around in anything electrical engineering for the last 30 years. And the main reason is everybody always assumes that once a power subsystem works, don't mess with it because it's working. And if you mess with it and something wrong happens, then it'll blow up all the chips that are actually downstream from it. So the level of innovation that has happened in power electronics has been on the relatively low side. Bulk of innovations in power electronics began to happen once we moved away from big hunking machines to laptops when power supplies needed to become smaller and smaller. That's when we saw power density becoming a key requirement. So we went from big power supplies to smaller and smaller power supplies to drive laptops, then power supplies to drive our cell phones, and then power supplies to drive data centers and cars and everything else. So I think it's on the cusp of innovations that will allow it to take a huge leap forward. And I think government needs to, at least government agencies need to understand at this point in time that it's one of the most critical things that we need to do from an investment perspective, primarily because the grid needs upgrading, especially in the United States. And if we're going to pull the kinds of power that we're thinking of pulling from specific areas of the grid, especially for AI data centers and other applications, including charging EVs, we need to make sure that that grid infrastructure is going to be available and ready to handle the type of loads that we're thinking of putting in its direction. So lots more research, lots more funding for universities, and combined programs between universities and commercial companies like us. So we have, two universities that we work very closely with to drive these type of innovations in the United States.
Excellent. Thank you, Dinesh. Jeff?
Yeah, I think you need to understand that power is the food of electronics. It's and like it or not, electrical systems are fundamental to our society today. We don't have stable operating country or in neighborhoods, things like that, without a stable power grid. And as we have more and more intelligence embedded in dependence on these data centers, EVs, things like that, as much as we have policy around food for us, we need to have policy around power for electronics. Investments in making the more reliable and making the grid more sustainable, and making sure that the things that our society has become built upon are enabled and fed in the right way. So when you think about the policies that we have for food, think about the policies for power electronics as well.
Excellent. And finally, Pradeep?
Yeah, I think I would just add that, obviously a lot of attention goes to where's the energy come from, right? The power grid or other energy sources. And I think that's important. But without power semiconductors and the foundational chips that go along with them, you're not going to get from whatever energy source you have to whatever AI processor you're trying to power. And so it's a critical part of our overall strategy And I think policymakers need to understand that. And I know we focused a lot on, wide bandgap power semiconductors today, but there's a lot of foundational chips that go into really enabling it. I think one of the other panelists mentioned, things like gate drivers and microcontrollers and all this kind of stuff. We need to make sure that we have robust policies around all of that.
Excellent. And I'll use this as my cue or launch pad to let our audience know what advocacy or policy recommendations are available to them. Starting from the top left, and we'll go row by row. So SIA does have a emerging resilience report that kind of documents the whole of supply chain, walks individuals through fabrication capacity to back-end manufacturing facilities as well. So if you're curious about where are chips being made, where are they being assembled, and where are they being sold to, that is probably a go-to resource. The next major publication that we've had has been the Attracting Chips Investment, which is a guide for policymakers on how to attract industry investment into your economies. It looks at some of the market factors as well as some of the incentives necessary to bring the industry to your country, state, etc. The next thing SIA and member companies would like to highlight is the R&D programs paper, that documents a little bit of the R&D ecosystem in the United States and gives policymakers or members of the public a little bit of information as to how to improve R&D spend and how that may contribute to wider prosperity. And finally, the last policy report we'll highlight today is the Chipping Away report, which looks at some of the labor economics, market gaps, etc., that exist and impact the industry. So if you're looking for more information, please feel free to connect with us. Our final slide is a brief thank you with my email address. If you are a member of the public and you have any questions, please feel free to get in touch. I'll be happy to hopefully have an answer for you or route you to a member company for further information. With that said, we'll conclude our presentation today. Please join me in thanking our distinguished panel. So Paul, Dinesh, Pradeep, Jeff, and Leonard, as well as all the people on the back end that have helped make this happen. Special shout out to Saloni Genkar and Dylan Peterson. With that, thank you, everyone.